Let's move to the next presentation, which is statistical peculiarities of the mechanical response of loaded solids at the pre-fracture stage. And the lecturer is Igor Smolin, correct? Okay,
yes.
Please.
Thank you very much, Mr. Chairman, for introduction. I will present you our work, which was performed by scientists from two organizations, Institute of Strength Physics and Material Science. Sorry. Does it work? No? Yes. Maybe oh, switch off. And from Tom State University, and my coming here was due to financial support from Tom State University. Thank you very much. Mendeley Foundation. So here is a brief outline of my talk. From the beginning, I will introduce some concept of evolutionary approach, which is developed in our group. And we'll give you some examples of evolution stages during deformation until fracture. The next point, the results of the experiments to identify the stages in the examples of two materials, marble and ceramics. And the last, some discussion and conclusion. Here are presented some papers from our leader, which give you an outline of evolutionary nature of destruction of solids in media. In general, it can be said that due to this theory, we present any solids or media under loading as a non-linear dynamical system, and which is typical for such a non-linear dynamical system is to see two different stages in their evolution. The first stage is quasi-stationary mode, and the next is blow-up mode, which is very fast and is accompanied by increase of some parameters and localization in time and in space of some parameters of the system. It is very important to introduce positive feedbacks when we try to model such system and to understand their behavior. Just these positive feedbacks give results in localization in time and in space for some parameters. And when these parameters become infinite in a finite time interval, we talk about so-called blow-up mode. This blow-up mode, this term was introduced by Russian scientists from the Kaldych Institute of Applied Mathematics, and here are some examples of their papers which are devoted to this theory. So when we say about the evolutionary approach concerning deformable solids, in our group we have performed a lot of numerical calculations of deformations of various specimen and media using evolutionary constitutive equations. Those results of those calculations have shown that for non-elastic deformation fracture, we can observe evolution of studied objects as in nonlinear dynamical systems. And in the last 3 years, we have performed some experiments, and this talk is just devoted to these experimental results. So the purpose of this talk is to analyze the data on the dynamic response of loaded samples of brittle material, which I have mentioned, from the viewpoint of nonlinear dynamics. This slide is devoted to an example of evolutionary constitutive equations. We introduce here damage evolution. Here are the explanations of notions. It is important to introduce nonlinear functions just mentioned to. It is very important to have a power law type of functionality, which is typical for evolution of many dynamical systems, which have been shown in papers by Maleninsky and Potapov. Of course, it is here it is shown that damage is proportional to damage which have already accumulated, and also depend on the stress which is in the solid, and the stress state, which is here, is characterized by the Lode parameter. Here is an example of calculated calculations which is performed using this damage model, which is in this slide expressed in non-dimensional parameter, which is typical for damage evolution. You can see that we have a very pronounced long stage of quasi-stationary evolution when the damage is approximately zero, and in the last it is very fast growth or increase in damage, which is just an example of blow-up mode. And now what we have revealed in our experiments. I would say the type of experimental investigation, we have used 3-point bending and uniaxial compression, which were performed using marble specimens and porous alumina ceramics. We used universal testing machines of this type, and to analyze the response, dynamical response of these materials, we used a Polytech laser Doppler vibrometer, which allowed us to measure the velocity at a point on the surface with the following characteristics. Frequency from 48 kilohertz to 250 kilohertz, and amplitude of the velocity is up to 0.1 micrometer per second, and the diameter of the laser beam spot is about 50 micrometers. Here is outlook of this experimental setup. Here it is light laser head, and then a sample under bending. So the results for marble. Here's the dimensions for the samples, for bending and for compression and bending. Those results were published in some of our papers. This is an example of response. You can see that we have a long quasi-stationary mode when we have only noise in our measurements, and at the end we have a blow-up mode which corresponds to failure of the specimen. When we look in more details of this response, we can see that at the stationary mode we have some noise, which can be seen also in this time period. And then we have a study of increase in response of velocity of the specimen sample. It can be seen in details for next period of time and in the last period of time. The time of failure in this example is this value. So when we try to estimate the duration of blow-up mode is to from 100 milliseconds to 20 milliseconds, depending on what threshold we can choose. In this slide, you can see comparison of experimental and calculations which I mentioned at the beginning when I talk about damage evolution law. You can see that the response is quite similar when we using non-dimensional damage and non-dimensional velocity. The next type of experiments was we use bending. The first one was with compression, and here it's bending of marble specimen. You can see that in this case we doesn't reveal blow-up mode. We only can see that there are some increase, not non-linear, but rather not so fast, I would say. The maximum velocity is on order of magnitude smaller than in compression, and the duration of the stage is much shorter. And also we can see non-monotonic increase in velocity with some decrease in velocity magnitude. The next part of this presentation is connected with the results for aluminum ceramics. Again, dimensions for samples. They are rather similar with marble. And now, bending of ceramics. Again, we can see rather long quasi-stationary mode. But when we approach failure, we can distinguish some increasing of velocity, but not so fast and not so strong as for marble samples. Here are the examples of specimen after failure in bending. You can see that we have different crack shapes.
3 minutes.
Okay, thank you. And corresponding to these very different shapes of cracks, we can see different response in velocity also, of different sign and of non-monotonic increase in velocity. In logarithmic scale, it can be seen that it is not power law of increase in velocity, but rather changing of magnitude of response. So we call this stage as stage of pronounced monotonic increase in velocity. The duration is about half a millisecond. Compression of ceramics. Again, we can see the fracture, which is not can be distinguished as blow-up mode, but only increasing in oscillation of velocity. But in this case, we can see peaks corresponding to chipping of more brittle ceramic specimen comparing to marble. And these peaks correspond to decrease in long loading time diagram. The last part is of my presentation is just devoted to an estimation of statistical parameters. We try to analyze the response of marble in compression, which is similar to blow-up mode. We have analyzed this response as using the time series analysis, and it have shown us that this response in this case is correlated rather good, which we can see from autocorrelation function, and even correlation with the last part, which corresponds to blow-up mode, is rather good, but not but in a rather short period of time just before fracture, before failure. Rather interesting in analyzing of fast Fourier transform, which was performed in so-called 2D photograph. In this axis, it is imaginary and real parts, and it reflects some multi-scale character of deformation process. Using wavelet transform, we can distinguish just short peaks in response in the signal, but not very important for the analysis of nonlinear dynamics here. Here are some conclusions. I would say that, at the end, I would say that it is important to distinguish two stages of dynamical response to loading, which we have revealed from the analysis of surface of samples using laser vibrometry. And there are some numerical, some numbers which correspond to marble and ceramics materials in compression and in bending. Thank you very much.
Thank you very much for the presentation.